Well, thanks first to the organisers for the opportunity to speak, because I think this is a little bit different from, well, certainly the talks I've heard so far today. I think the main point about this slide is to note that if you want to learn, if you're at all interested by what I say, there is a paper on the archive. Unfortunately, I can't be here tomorrow, so if you want to ask me any questions, my email address is down there. I thought I would try to explain, in a sense, what I want to talk about by starting with a rather long quote. I'll read it. I'll read it myself, so don't bother reading it yourself. But from somebody who's been mentioned a number of times today, so I guess he's a pucker person to refer to in this meeting, and that's Rob Speckens. So I'm reading this because it very much summarises my own kind of inspiration and motivation for this, for the work I've done in this area. So he says, this is I think it's as yet unpublished document on the Perimeter Institute. In the standard framework of hidden variable models, it is assumed that a preparation procedure creates or prepares a system with certain intrinsic properties. However, if one adopts a radically relational worldview, then a system's properties are only defined relative to everything else in the universe. Because the measurement device is part of the rest of the universe, as one brings one or another measurement device up to the system, one is changing the rest of the universe, and consequently the assumption that the system has the same properties in these counterfactual scenarios is simply mistaken. It is conceivable, therefore, that dropping the assumption of intrinsic properties in favour of relational ones within the hidden variable framework may lead to a more sensible, realist interpretation of the formalism. So, as I say, that's been very much my sort of physical motivation as well. Is there a way of approaching our understanding of quantum theory from within a hidden variable type of approach, but one which encompasses this notion of what Speckens calls radical relationism? And the question initially one has to ask is how could one ever formulate this idea mathematically? Certainly if one tried to formulate it within the sort of conventional framework of physics, i.e. sort of differential equations or different equations or something like that, one is inevitably faced with the sort of grotesque non-linearity which Einstein, of course, railed against, and which we know is inevitable from quantum theorems. So my approach has been to try and think of alternative ways of encompassing this type of, let's call it radical relationism, in a mathematically sensible way, but one which is not based on differential equations, but is in fact based on geometric ideas. And geometric ideas in what I would call state space, or phase space, if you like. So I'm proposing something which is to be thought of as a kind of a new principle, if you like, in physics, if you like, an ontological principle, which talks about the notion of what constitutes states of physical reality and what doesn't. I'll try to explain this, but let me just say it sort of crudely, or state it boldly rather. This hypothesis, what I'm saying is that I'm defining states of physical reality as belonging to a certain subset of state space. By state space, I'm thinking classically, just think classically in terms of, if you like, phase space of an n-particle system, but more generally state space. So states of physical reality, I'm proposing, belong to a certain subset of this state space. And this subset has a certain invariance property in the sense that there are some underlying deterministic causal dynamical equations, which I'm calling d subscript I, which leave this invariant set, which leave this subset invariant or invariant. The subset is invariant under the action of these dynamics. Now, the particular dynamics will be chaotic, and so the subset will have this fractal property to it. I'm just going to illustrate this in the context of a toy model, which is the famous and prototypical Lorentz three-component model. Now, in standard dynamical systems theory, one usually thinks of the differential equations as the primitive thing that you're given, and you can start those equations from any point in the system state space, which is three-dimensional here, and you will find that after a while it asymptotes to this fractal invariant set, in some sense reaching it asymptotically. So it's called an invariant set in the sense that if you initialized your equations on that invariant set, then it would stay on that set forevermore. And more generally, a point on that invariant set, the past history has always been on the invariant set, and the future history will always be on the invariant set. Now, what I want to do here is think about things, in a sense, the other way round. I want to imagine that we are given this subset by some other means than the differential equations, by some geometric rules. And in some sense, this geometry is considered to be the primitive idea that I want to put over, rather than the differential equations. And in some sense, the differential equations I want to think of as just subordinate to the geometry. For example, in the case of the Lorentz model, there is the Lorentz invariant set. One can use, for example, ideas in knot theory to characterize the structure of that invariant set. So there are various theorems which say these knots describe the so-called unstable periodic orbits which lie close to the chaotic attractor, and the whole character of the Lorentz attractor can be given in terms of these the structure of these knots. The point, the details are unimportant here. What I'm saying is we have an alternative means of specifying the invariant set in some sort of geometric way, and then I want you to think of the differential equations as being somehow subordinate to that. They're just describing motion on the invariant set. The point about this is that it then gives you a special sort of privileged, the invariant set has a special privileged status. Points on the invariant set are primitive beings, if you like, and points off the invariant set have a different character. Whereas if one starts with the differential equations, then in a sense, at any point, the differential equations can be applied to any point in the three-dimensional Euclidean state space. There's nothing in the structure of the differential equations which sort of distinguishes between points on or off the invariant set. So this is the key point I want to somehow apply to this notion of the state space of the whole universe, and the hypothesis being that this structure of an invariant set has some preordained or primitive geometry is inherent to physics. Now, the motivations for this idea, I suppose, are manifold. One is, of course, all of physics is, the bedrock of physics is invariance and symmetry. So the notion that this subset has a special property, which is invariance, it leaves this dynamics, it is invariant under the dynamics, that sort of gives it a special invariant property, which is, as I say, invariance is a basic primitive notion of physics, so it sort of fits in with what we think in general terms. My own background is sort of very much in nonlinear dynamics, and I suppose I have to say that these types of fractal invariant sets in state space are really very beguilingly beautiful mathematical structures, and it's always seemed to me a shame somehow that they don't play they apparently don't play a more fundamental role in physics. So this is, I suppose, an attempt to try to bring some of this idea into physics. Well, a kind of basic question one has to ask, however, is, well, what could be the underlying physical process which could generate such a invariant set in terms of the universe as a whole? And my hypothesis is that gravity provides the physical, if you like, the process. So we know in nonlinear dynamics we need three essential features to get a chaotic system. The system has to be nonlinear, has to have some sort of instability, and crucially for fractal attractors or fractal fractal invariant sets. Fractal meaning some fractional dimension, a smaller dimension than the total dimension of state space itself. One needs some form of irreversibility. Now, in the case of the Lorentz equation, and for most dynamical systems with fractal attractors, one uses, or one invokes some sort of notion of dissipation. Now, normally dissipation is considered a phenomenological process, and so apparently doesn't have a role in fundamental physics. But again, here I want to draw on ideas in black hole dynamics, which in the lack of time, I'm not going to be able to describe in any detail, but I refer you to books of Roger Penrose, eminent emeritus professor here at Oxford, who's written extensively about the irreversible nature of black hole formation and evaporation. So I'm using, again, gravity through the idea of black hole irreversibility as my surrogate for irreversibility, not my surrogate for dissipation or energy dissipation. Instability is a widespread feature in gravitating systems, right up to cosmologies, such as the Bianchi type 9 cosmologies, and general relativity is explicitly nonlinear. So gravity kind of provides some of the basic motivation for this, and of course the other motivation is it may give us a new perspective on quantum physics, and in particular on this notion of radical relationism that Speckens spoke about in the quote earlier on. So a simple fractal set is provided by the Cantor set in one dimension. Just take the interval between 0 and 1 and systematically remove middle thirds. I'm sure you're all familiar with this. Now you end up with a set which has an uncountable number of points, but it has measure 0 in this interval. One way of expressing the points on the set is to write a point in base 3, and it'll be on the set if it only contains the digits 0 and 2. So there's a kind of random point on the Cantor set which just contains 0s and 2. So it's a kind of special number in the sense of all the numbers on the real, in that unit interval on the real line. Now suppose we were to randomly perturb that point on the Cantor set. Now what does random mean? Just choose randomly a number on that interval, and by definition if it's random it'll have an equal number of all of the three, so again writing it in base 3, it'll have an equal number of all of the digits 0, 1 and 2, and then if you perturb that original point on the set with this sort of random perturbation, you've destroyed in a sense the specialness of the point on the set, and you'll end up taking yourself to a point off the set, off the Cantor set, to somewhere, in fact somewhere generally which will be isolated from the Cantor set, so there actually exists a neighbourhood around that point which will not intersect the Cantor set. Now these, in general, these invariant sets I'm thinking of, like the Lorentz attractor, can be considered locally as a product of a smooth curve, which is the trajectory on which the states evolve, multiplied by this Cantor set, which could be described as a nowhere dense measure 0 set. And again, the idea is that if you randomly map or randomly perturb a point on the set, you'll almost certainly take it off it to a point isolated from that set. So with that in mind, I want to kind of come to some of these sort of more quantum mechanical types of issues. So, for example, the issue of counterfactual measurements. So Alice measures the spin of an electron, does an experiment, has a definite answer as measured by the Stern-Gerlach apparatus. But now we ask the question, as is inevitably the case in all of these types of contextual or non-local theorems, what would have happened had she measured the spin of that same electron in some different direction? And the idea is to apply that sort of thinking of the random perturbation to this more sort of worldly example. So again, we consider when we, in thinking about this counterfactual type of experiment, we consider a hypothetical. It's not one that actually occurs, but we're imagining it in a theoretical sense, a perturbation which is keeping that electron, as it were, fixed before it enters the apparatus, but we're trying to imagine changing somehow the orientation of the apparatus in some sort of theoretical sense. So in a sense, what we're doing, if we imagine the orientation of the apparatus as defining some direction in state space, then we're imagining some perturbation along that measuring apparatus direction, keeping everything else, as it were, fixed. Now, if we invoke... so in standard physics, in a sense, all of state space has an equal right to exist. There are no preferred, there are ontologically preferred points in state space. So, and that type of perturbation P would be considered to be perfectly sort of theoretically at least justifiable. And in fact, Ter Hooft has written a paper on what he calls the unconstrained initial condition constraint or something, which would allow that type of perturbation. And this is in a sense why I have postulated this invariant set hypothesis as a mathematical sort of construction, because under the conditions of it, that perturbation, that dynamically unconstrained perturbation, we're just doing a thought experiment of imagining rotating Alice's apparatus or perturbing the state of the universe along that direction, keeping everything else fixed. And by this notion that the invariant set is a measure zero, no dense set, you're almost certainly taking yourself off that set. And if you have, by the hypothesis, said that states of physical reality are just those on the invariant set, then by definition you've taken yourself to a point which is not a point of physical reality. It's in some sense an unreal point. And so you cannot say it is either true or false that in reality Alice would have measured the spin of that particle as up for this different measuring apparatus. So using this idea of geometry in state space, and again I stress the idea that it's this geometry which is to be considered the kind of primitive concept, and that the dynamics are something which are sort of subservient to it, which operate on that geometry. Using that idea, we can, I think, get some mathematical start to approach mathematically this idea of Speckens, of radical relationism. Because what I'm saying here is true, in a sense, for any of the directions in phase space. It could be the direction, it could be associated with what a bug-eyed monster in Andromeda Galaxy has for breakfast. It makes no difference whether we change that direction in phase space or Alice's apparatus. The same point applies, that a hypothetical, dynamically unconstrained counterfactual perturbation will take you off the invariant set and hence to a state which you cannot call a real state under the conditions of this hypothesis. Okay, so I want to just move on now to sort of ask the question that can we sort of get to grips then with this picture about what, this is perhaps the central kind of conundrum, I suppose, in quantum theory, what really is the meaning of these kind of superposed states in quantum theory, and does this hypothesis tell us anything new or different? And my proposal is that, well, perhaps it does. Now, of course, the first thing one learns in quantum theory is you cannot just assume that this is a probability that the system is either red or blue. We just don't know what it is. In reality, it is either red or blue, and this somehow just expresses our ignorance of that property. Because of quantum coherence, this really is to be thought of something different from just the system being either red or blue. However, what I want to propose here is that we do actually interpret this as a probability, as a frequentist, sort of the simplest type of frequentist type of probability, but only, and this is the key point here, only for these states on this invariant set. This is just supposed to be a kind of crude idea of thinking of you know, at perhaps an instant in time of the, no, not in a certain projection of state space, and I've somehow partitioned the invariant set into either blue or red. This is supposed to be a fractal in a sense. So as you zoom into a blue, what you think is a blue region, you might find red regions embedded in it, and then if you zoom in further, there might be blue yet again. And in fact, perhaps one can think of, because the square root of Planck's constant has the dimension of a phase space dimension, one could think perhaps of this neighbourhood as having that type of dimension. So I'm thinking now of this idea, well, okay, so first of all, let's just imagine we can somehow partition the invariant set into red and blue. So green is supposedly points not on the invariant set, but it's just a schematic diagram. And we can also perhaps think using, again, dynamical systems theory, perhaps these red and blue points label what might be called basins of attraction to some stable or quasi, they can't be completely stable, but some quasi-stable regimes, which could be called R or B. So if a point is red, it will tend to be captured by some sort of relatively stable part of the invariant set. Remember, these invariant sets are non-linear, so they have regions of stability and regions of instability. That's an inherent part of their non-linearity. So I want to investigate the question, or explore the question. Let's interpret that sort of apparently quantum mechanical looking object as just a probability within the neighbourhood of the invariant set that a point on the invariant set, or a point in the neighbourhood, is red or blue. And in my particular construction, I'm thinking these red points are red because they're in the basin of attraction of some quasi-stable regime R, or they're blue because they are in the basin of attraction of some quasi-stable regime B. So we can talk also of this probability as being a probability of either being red and evolving to R, or blue and evolving to B, or equivalently using, again, suggestive language to something like what one might call quantum mechanically an entangled situation. So the question is, can we relate this to something like that in quantum mechanics, where Alice measures the spin of a particle? Now, in quantum mechanics, I mean, by construction, if you like, if this idea of if this notion that an invariant set really does exist, which it may not do, but I'm supposing it does, obviously quantum mechanics is blind to its existence. There's nothing in quantum theory which says anything about invariant sets. So there's nothing in quantum theory to tell you whether a particular state, if you like, or a particular measurement direction corresponds to an actual one or a counterfactual one. We don't know in advance of time which direction Alice will actually measure the spin in. So quantum theory is blind to the invariant set. So quantum theory has to, in a sense, deal with states which are on or off the set. So how can we link this idea of frequentist probabilities on the invariant set to this quantum mechanical notion? I want to just in 3 minutes then use an analogy, which is, so if we go back to the Stone Age, sort of Stone Age mathematicians, they understood, well, if these were stones, they would have understood that these are three marker pens, but these would be 3 stones. So they kind of started using numbers to describe how many objects they were holding, or the fact that this set of pens had one more object than this set of pens. So that's fine. So counting numbers. And then along came the mathematicians, and then they said, well, okay, that's very interesting, but if we take the basic algebraic properties of integers, integers have interesting algebraic properties. We can add them, we get another integer, we can subtract them, we get another integer, we can multiply them, we get another integer. So people like Gauss said, well, let's forget about the fact, let's not worry too much about the fact that integers are things that can be used to count objects, but just use these algebraic properties. And then we can move the integers off the real axis, you know, into the complex plane. We have a whole two-dimensional grid of integers which are defined algebraically. Of course, these integers no longer, 3 plus 2i, no longer describes the number of pens in my hand. So if I was told that a particular point on the grid actually corresponded, say by some experiment, to a number of stones in a pile, I would know that that point corresponded to a point on the real axis. So I want to sort of propose here that the reason we have this abstract Hilbert space formalism in quantum theory is, in a similar sort of way, it's a need somehow to be able to move off the invariant set in a consistent mathematical way. Well, we can't do that keeping this original primitive idea of frequentist probability. We know we can't do that because that will violate all of our ideas of contextuality and Cognos-Beck and Bell and so on. But what we can do is, like Gauss, we can move off the real axis if we keep just the algebraic properties of probability. So in my view, that is a way of kind of reconciling the notion that quantum mechanics may well have a profoundly realistic interpretation and maybe kind of something one can seamlessly join onto our standard theory by using this notion of abstracting the quantity moving off the invariant set. So just 1 minute finished. So I'm sort of proposing here 3 levels of reality. Oh yes, I just do want to say one thing which I haven't said. 3 levels of reality. First of all, there is, my claim is there is a kind of deterministic ontological reality. One of the interesting things which I haven't talked about is that these invariant sets are technically non-computational. So they're not things we can compute precisely, and I'm claiming that we can either compute them or not necessarily experience them directly, but they are there. Quantum theory is a sort of a weak, what I call a weak coarse graining of this invariant set. And the Schrödinger equation on this invariant set is nothing more than a Leuven equation for conservation of probability for these ontological state trajectories. So only when you move off the invariant set that you start to get into the more abstract notion of the invariant of the Schrödinger equation as an operator on Hilbert space. The final point I want to say is that there is a third level of reality which comes out very, I believe, very sort of simply from this picture, which is the classical world. If you take a fractal measure and just do a very, very long time average, for example, and just ask what does the measure look for those very long time average states, by the central limit theorem, you'll just end up with a continuum measure. You'll end up with, say, Gaussian. Once you have a continuum measure, then all of these issues of contextuality, the fact that, you know, if you move in a certain direction, you move off the set, they fail, because a continuum measure, now all points in state space are allowed. And so in this highly sort of coarse-grained limit, you end up with classical physics, classical deterministic physics, which is exactly what we see. So my picture is, let's put this in. So my picture is we have this underlying ontological theory, and we have classical theory. In some sense, quantum theory lies between it. Now, the standard route which we've tried to take to find these things and these things is through the language of differential equations and difference equations. And my claim is that that's the wrong route to take. It looks like a short route, but it's a highly sort of singular route, and I think this is why we've had so much difficulty. And my claim is that going through these geometries in state space, we have a much conceptually simpler, I think, picture of how quantum theory might link both to a deep deterministic theory of physics on one level and the classical theory on the other. I'm going to miss over these points. I'll just stop with another sort of inspirational quote from another perimeter guy, Chris Fuchs, which again sort of stirs my heart when I read it, and it describes what I believe to be true. So this is from the book which he contributed to. The task is not to make sense of the quantum axioms by heaping more structure, more definitions, more science fiction imagery on top of them, but to throw them away wholesale and start afresh, we should be relentless in asking ourselves from what deep physical principles might we derive this exquisite structure of quantum theory. These principles should be crisp, they should be compelling, and they should stir the soul. So, I don't know whether I've stirred anything, perhaps I've enraged you more than stirred you, but my proposal is the invariant set hypothesis may be one such principle. Thank you.
We probably have about 30 seconds for a question. I think Professor Werner was first.
So there's a bit of a discrepancy here with talking about an invariant set, and you seem to look at cosmology at the same time. So clearly there is no time invariance there. So why use this concept of really invariant sets? I mean,
I don't mean time.
It's something so complicated we don't want to look at it. Right? That's the basic thing that we require for your argument. You don't have to. So invariant set really is metaphorical. So something looking complicated.
No. I mean invariant in the set that it is a subset of state space, and once or if the state of the system lies on that set, it will stay on it forever and has been on it forever. So it is invariant under the dynamics. So I don't mean it metaphorically, I mean it in a precise dynamical way. It's not invariant in time.
And we don't have to be bothered by entanglement because Alice can never make experiments that we are not free to choose the devices, right?
There are implications about what we're free to do, but
like for Torf, that's it. I mean, he likes the Torf demon. I proposed that to him. So the initial condition of his cellular automaton is God, really.
Yeah, what I'm proposing, for example, if you do move from one point on the invariant set to another, you've almost certainly perturbed all of the degrees of freedom in the universe. So you've changed Alice's measuring apparatus and, in fact, the electron and the bus that passes. You can't make. It disallows these kind of counterfactual experiments.
It's always predetermined what you want to do.
Well, it's not this set is in a sense a very, sort of outside time in a sense. It's something existing in state space, which we're proposing. Well,
no, exactly. For Torf, it's really religious.
Well, it's nothing religious.
I don't think invariant sets need to be religious. That's our half hour, I'm afraid, folks. We need to hand over to the next speaker now.